pretty amazing to me because I would have expected there would have been some dominant person who was unbelievable and that they brought their team along. But so this is very good. So that means I guess there's a chance that the champion would be a two-time winner if they could win today. So we'll see whether that happens. Before we go any further, I wanted everyone to thank Tanzir, okay, over in Bangladesh for fixing up, for doing all the contests. So let's give a cheer to Tanzir. He has been good. Okay, any discussion people want to have about the contest? Okay, is there a question people want somebody else to answer? Any general discussion? Yes?
I would like to see if somebody here solved the problem 8, leaving the bar, because I had an idea and I don't know if I was right or very, very, very wrong.
Okay, so who left the bar? I don't know if this is a country where people leave bars. Okay, it's my, okay, who? Oh, that's my understanding. Okay, so here, why don't you try this? I don't know if this is working, actually. Try that, bang it.
Oh.
Good, okay, good, go.
Do you have a marker?
A marker. Yeah, any of these is fine.
So I think there's many different solutions to this problem. We were talking about them yesterday. But let me just explain the problem first. We were given 10 to the 5 or fewer points, I believe. And these are points in the plane, so they are like x and y. And what we know about these points is that their coordinates are up to 10 to the 6. And actually, it's more than that. We know that when we treat them as a vector, their length is up to 10 to the 6. So that's kind of a unique constraint. And what we're asked to do is for each one of these points, which is probably better to think of as a vector, we have to decide whether we add it or we subtract it. Okay, so let's say this one, instead of adding it, we got the opposite, we subtracted it. And we can kind of think of that like putting it right there. That's like vector subtraction. And then let's say that this one we add as well. And we end up with something like this, right? What the problem asks is choose for each vector whether you add or you subtract such that the final point that you get after you all those operations is within a circle of radius 1.5 million, right? So 1.5 times 10 to the 6. Is that clear? Okay. And what you have to output is just for each one, whether like 1 or -1, depending if you added or subtracted it. So there are many, many ways to do this, and you can cheese this problem. Yeah, it looks like the test cases are very weak on this problem. So you can do some not so legitimate stuff and still get accepted. So what we did was observe that in one dimension, this problem is pretty much trivial, right? So you're given some set of numbers, like, I don't know, 30, minus 10 to the 6, and so on. And what you want to do is add and subtract and get some value that's in total. Say you add, you subtract, and so on. And in total, you want to get like something that's less than 1.5 million, right? And this is a trivial problem. You can do greedy, and this will never fail. Because you have some strip of length 3, that's your allowable range, right? This is 0, this is 1.5 times 10 to the 6, and so on. Minus 1.5 times to the 6. And you only ever have to move 1 unit, or like, well, let's just rescale everything 10 to the 6, because that's easier, right? So you only ever move 10 to the 6, right? Because these numbers are 10 to the 6, and you have to move like either left or right, you choose. And of course you have 3 units of distance in total, so there will always be one side that's at least 1 unit away. Sorry, I keep saying 1, I mean 1 million. So I'm just going to remove the million here. It's way easier that way. So I have this thing that's 3 long, and you have to move 1 either to the left or to the right, and you choose the direction, right? And since one of the 2 endpoints is always at least 1 unit away, you can just move towards that endpoint, right? And you always pass. Is this clear? Yeah. Okay, good. So the idea is, well, that's really nice and easy. So let's try to do this for the original problem. How can I make my original problem look more like this, look more one-dimensional? So the idea was to split these vectors that they give you in the input into thin strips. So we just pick some sort of cone, like this, with some angle, theta. We group the vectors in there, and we solve using the greedy algorithm. And the idea is, like, if we make this angle small enough, then it almost looks like a straight line, right? And so the greedy, it might not be exactly correct, but it would be pretty good. I don't really have a bound on how far outside the region we can go, but I don't think you can fall out of a 1.5 region within just one strip using the greedy algorithm, right? But so then the idea is, well, I solve each one of these strips, and I get a vector out of it, right? So the solution to each one of these little cones is going to be a vector. But I'm not going to split it like too small. I'm just going to split it into 20 different little cones. So I'm just going to get 20 little vectors. And now we have to solve the same problem, right? The input problem, but only 20 vectors. And this one I can guarantee an optimal solution quite easily, right? Like we can very easily just try every possibility, like add or subtract, all the 2 to the power 20 options. And for every little vector you get out of each slice, you just try, do I add or do I subtract? All the 2 to the 20 possibilities, and you pick the one that's closest to the origin. And that passes.
Okay. Okay, thank you. Okay, one question. This is actually now an important question for today's lecture. How many of you look at this problem and immediately see that it's NP complete? Okay. That's okay. I think one person, the one who was cheating, or maybe you're just lifting it because your arm is broken and you can't bend. Yeah.
Finding the minimal solution is complete, right?
Right, okay. How many people saw that? Okay? A couple, okay? My hope is that today you would see this if you, is the kind of thing that maybe you see. And I think that it helps you to see that. It may or may not help you with this particular problem or yada yada, but that's going to be kind of the focus of today's class, okay? So we'll remember this. Hopefully we'll get to the point where I'll show you how easily it is to show that this one is NP complete a little bit later. Any questions? Okay, any other problem people have a burning desire to do? Yes? Problem, which one was it? C, large triangle. Only 5 teams did it. Did any team do the large triangle one that is here? Did any team, you want to talk? Okay, anyone who wants to talk is allowed to come up and talk. And you're allowed to talk. Come. Use your here. I think it's just on.
Okay, this was problem C, I think.
Yes, see.
So, the statement is in problem C. You get n points, which are 2,000 points at most, and you get a number, which is an area, represents an area. And the problem is simple. They ask you to find 3 points that form a triangle with area S. Now, of course, you can do this easily in cube. You just try all triangles. and check if it forms an area. But this doesn't pass, so you try something smarter. And I like this problem because you can solve it using a technique that is, I think, really cool and is like not so popular. It's called all pair points. I will write it down. So the idea behind this technique is that you try, you make a list with all the pairs of points. So, different pairs of points. I think these are too many points. So, for each pair of points, you form a line. Like here. I will not write the direction. There are about n squared lines here. And you just sort them by angle. So I guess here, you have to start somewhere. I will start in the x plus direction. This one will be the first line. I think this will be the second line. And then we will, I don't know, go up to here. You have to choose like a direction for every line in order to do this. You usually just try both directions and you treat them separately as different lines. Like they are really vectors instead of lines. But we will just do it like this, I guess. I don't know if the numbers are too small. Do you all see the numbers? Okay. So the idea is you start from line 1 and sort all of the other points with respect to the line, like in signed distance. So you start, like this will be the first point because it is the farthest to the left of the line. And then this one will be the second point. And then I guess these 2 points are the same distance. And the idea is that you go, the lines are sorted by angle. So you go line by line. You move from 1 to 2. And here in this example, you can notice that when you go from 1 to 2, in order to keep the list of points sorted, you only really have to care about point 1 and, this point and this point. And this magically generalizes to higher number of points on all examples. Every time you switch from a line to the next angle, from one angle to the next, you only have to swap 1 pair of points. This is the idea. So for the n squared vectors or lines, you just swap the points and you keep a vector of all the other points sorted with respect to the line. And now this is a bit hard to explain and prove, and I will have to be a little while here drawing examples and explaining why this happens and all the stuff. It even works with collinear points. It keeps, you have a lot of points here, it keeps some internal order of the points. Some of these are really to the left of the line and some are to the right of the line, and it's consistent. But it's a bit hard to explain, so you will just have to read some blog about this technique. So I will assume that we have this technique and we can just go through every line with the rest of the points sorted with respect to the line. And once you have this, it's relatively easy to solve the problem. Because if you have a line and you have all of the points sorted with respect to the line, now this line is between 2 points, right? We will call them A and B. And you want to find the triangle of area S, you can do binary search, right? Because this triangle, we will only consider points to the right of the line without losing generality. This triangle has less area than this triangle, has less area than this triangle, because the area of a triangle is just the base times the height. And the height is conveniently the same distance. You can just do binary search. Find the point which forms the exact area you are looking for. And you can see that in this way, you are trying all possible triangles in time n squared log n.
Very good, yeah. You got a question?
Yes?
First iteration, you have the points ordered from left to right.
Yeah, it depends on where you start. I usually start from left. The first line will be like in the x positive direction. So I will sort them by y coordinate.
Very good.
That's it.
Okay, thank you. Okay, any other last problem? Last problem that, if people feel the need for another one. Okay, going once.
Problem B.
B. B, do we have anyone, space rescuers? Did anybody do space rescuers? Want to talk about it? You're allowed to, or you're allowed to sit. This is a free country, as far as I know, okay? Not an expert here, but I believe that's true.
Hello?
Yeah.
Well, I didn't solve this in contest because I didn't read it, but I've seen this problem like many times. So I just like make it very fast and put it. Well, the problem said that you have different points in a 3-dimension, and then you have to create a new point that the sum of the distance of that point to every single point is the minimum as possible. No? Well, that. The maximum distance is as small as possible.
So it's like the centermost point. Is that what you're looking
Yeah,
for? Centermost point.
I don't know how to talk, but yeah, that's right. The way I look at this problem is that how would you solve it if you just have like one dimension instead of three? So if you just have like the x, you can see that if you want to create a new point, if you go like to infinity, it will rise like the solution, and if you go to the other way, it will go also. So when you're like getting closer, you will have like something like this.
Right.
And you can do like you can do two things. You can either iterate over the time that it's going to take the points to be there, and every single point will have like a range. And well, you can just intersect the ranges, or you can do a ternary search in this function that we have. Then you can think about it in 2 dimensions. This will also be true. So you have to like search for the best x, and then when you have like the 2 mediums, you will have to search for the best y, because it will also be like that function. But if you don't want to do like ternary search, you can intersect circles, because the ranges will be like this. Well, you're saying that they're going to meet like a time, like if you do a binary search instead of a ternary search, you will have the radius of where they can reach. You don't see it? Like they have like a velocity of 1. Yeah, you can see that you can say that you move, they all move at the same speed, right?
They move along what? And what moves?
Yeah, you can say they're going to meet at time 0, they don't move at all. Like the
Okay,
Yeah.
I see. Okay. So you say like, let's imagine there's some origin point, and points are moving towards that at constant speed. And the question is, when does the last one reach your point? Is that what you mean? Okay.
Yeah.
Very good. I see.
So that will create a circle, and you can just intersect the circles,
Okay.
and the binary search will tell if every circle intersects in one point or not.
Okay.
If that seems clear.
Yes.
And if you do it in like the third dimension, you just can do another ternary search or intersect spheres. I haven't done it. The circles I have, but the spheres no. Yeah.
Okay, thank you very much. Okay. What I'd like to now get, okay, by the way, did the winning team, Balanero, Camabrio, did you guys come in yet, or are you guys here? Or they just took off for the beach? Is that you or no? No. Okay, fair enough. Okay, what I'd like to talk about today for our last class is this idea of NP, lost my thing. Is this idea of NP completeness, which I know may be a controversial topic in here, because it's not going to immediately lead you to faster, better programming solutions. So you may say, why am I telling you this? Okay? I'm telling you this because I find thinking about reductions, the ideas behind how NP completeness works, this idea of transforming one problem to another, as a very important way that I think about algorithms. Okay? Last we talked about duality. Remember, we had this big fight about whether finding a point with 3 lines in it was harder than finding 3 points on a line. And the answer is they're the exact same thing. Okay? And the reason we know they're the exact same thing is we did a transformation, turning one problem into the other. And that is the idea behind NP completeness. And I find that the ability to do these kind of reductions and think in terms of reductions is just a very useful part of the way that I think about algorithms. When I saw that first problem, I immediately said, this is NP complete. And why is that? That's because I know something about it. It changes the way that I think about it. And maybe if you didn't see that it was NP complete, you'll see it. Hopefully you'll see it's NP complete by the time end of class today. That's kind of what my hope is. And so let's start with, I think, actually here's a question, just to get a better idea of who you guys are. How many of you have ever done an NP completeness reduction? Okay, about half of you, maybe less. Okay, that's good. Okay, how many people? So, how many of you think NP complete just means I have to use backtracking? Okay, okay. Some people may think of it like that. What does NP completeness mean? Okay, and the best example of what the idea of NP completeness means would come to this idea of, suppose many of you are going to go off into industry after you do this. You will have a boss. Your boss will look like this, because that's what all bosses look like. Okay? And they will ask you to find a fast algorithm for a problem. And perhaps you will fail. Okay? Maybe you guys are good. Perhaps you will fail. And when the boss calls you in and says, give me my fast algorithm, there are 3 kinds of answers you would like to give, or you might give. One is you can say, I couldn't find one. I guess I'm not smart enough to find one. Okay? Why is that a bad admission to make to the boss? They'll try to find somebody who's good enough to find one, right? What would be a better thing would be if you could rigorously prove that there was absolutely no way there could be a fast algorithm for this. Okay? And the trouble is that There's almost no problems in the world for which people can make interesting proofs that there's absolutely no fast algorithm for it. Probably the one lower bound proof that you guys have probably seen is a claim that sorting always takes n log n, right? That's something that you can kind of believe, okay, that there's a rigorous proof that you can't, under certain models of computation, sorting faster than n log n. But there's very few problems like that. And even that comes with certain weasel words, that it depends upon what model of computation you're using. And there's weird things like hashing and stuff like this, and maybe something, something else can happen. So the idea of NP completeness is to offer a guarantee that says, I can't solve this problem, but no one else in the world can, okay? Okay, why is this good? If you have a situation where you can go and say, look, boss, see that? That's Corman. He can't solve this problem. See that? That's Knuth. He can't solve this problem. Even Skeena can't solve this problem, okay? So don't fire me, right? That's the idea that we're going to use to prove a guarantee in NP completeness. Any questions about what that means? Okay, good. Now, again, the idea is that, again, there are a lot of problems which we don't know efficient algorithms for, and we don't have real strong lower bounds on. And what NP completeness does is it provides a way to show that all these problems are really the same underneath. That was what was good we did with the duality thing, right? Those two problems were really the same problem. And what NP completeness basically says is every problem that's NP hard, NP complete, is on some level really the same problem. Okay? And that I find kind of an amazing thing. And so the key idea here that we're going to use is this thing called the Bandersnatch algorithm. What is the Bandersnatch algorithm? Well, Bandersnatch is the name of a problem. Okay? It could be shortest path, it could be traveling salesman, it could be space invaders or whatever else you were doing on the board a minute ago. Okay? Let's Bandersnatch be the name of a problem. And let's let Bobilli be the name of another problem. What is the idea of the Bandersnatch algorithm? To solve Bandersnatch, the input to Bandersnatch is a G. What is G? Maybe G is a graph, maybe it's a string, maybe it's a bunch of numbers. Depends what the Bandersnatch problem is. It's the input to it. We're going to give an algorithm to solve Bandersnatch by translating the input of the Bandersnatch problem into the input of the Bobilli problem. What's the input of the Bobilli problem? It's of type Y. What is it? Maybe it's a string, maybe it's a set of numbers, maybe it's geometric points, I don't know. But it's whatever the input the Bobilli problem expects. But we've done this translation in a very, very special way, okay? Where if we call our Bobilli solver, turns out that your programming language has a Bobilli solver in it that will solve that problem, okay? And if you call, and we did this translation in a very, very fancy way such that the answer to Bobilli of Y is the same as Bandersnatch of G. If I can do that translation such that Bobilli of Y is always equal to Bandersnatch of G, then I can return Bobilli of Y as the answer to Bandersnatch of G. Does everybody kind of see that? This algorithm is called a reduction. Okay, and again, if you think about our duality case, that's actually an interesting question. I don't know how to solve. What's Bandersnatch going to be? Let's say Bandersnatch is tell me whether or not this set of points has 3 of them on a line. How are we going to solve that problem? We're going to translate it into an answer of the instance of the Bobilli problem. What are we going to use for Bobilli? Given a set of lines, is there a line where 3 points where three lines go through the same point. What's our translation going to be? Remember we had this duality transform yesterday? Where we magically translated each point into a line? The answer is, because of the magic of that duality transform, the answer of Bobilli of y is always the same as Bandersnatch of g. And therefore, this is a correct algorithm. Okay? Any questions about that? This is important to make sure we understand this at this point. Okay? So what does the Bandersnatch algorithm here mean? It could mean one of two things. If we have a fast Bobilli solver, what does this tell us about Bandersnatch? If we have a fast Bobilli solver, what does this give us? Gives us a fast Bandersnatch solver, right? But what if somebody gives you a guarantee that there is no possible fast way to solve Bandersnatch? It's impossible to solve Bandersnatch fast. I can prove it to you. Okay? This means you can't solve Bobilli fast. Why? Because a fast Bobilli solver gives you a fast Bandersnatch solver, and there is no way in the world that there is a fast Bandersnatch solver. So therefore, there is no way in the world there is a fast Bobilli solver. Does everybody see that? Yes.
Does it only go like one way? Like, is it bidirectional or is it?
Well, I would say is it bidirectional? Let's just think about it. What?
It's an implication. I'm just making sure.
Yeah, so let's just think about it. Suppose, let's say, I want to solve sorting, and I find a way to translate sorting into the traveling salesman problem. Okay? I could show what? Okay? What does that show? If I can translate sorting into the traveling salesman problem, what does that show?
It's at least an log n.
Maybe. I would say it gives me a slow way to solve sorting, right? Does everybody kind of see that? If I'm using traveling salesman as my sorting problem but the two interesting implications are, if Bobilli is fast and my translation is fast, then Bandersnatch is fast. And if there is no possible way to solve Bandersnatch fast, this is enough to prove that there's no possible way to solve Bobilli fast. That is the reasoning that we're using here. Any questions about that? Okay. So what you call it? Again, this is basically what I'm sort of saying. That if Bobilli is fast, we can solve Bandersnatch in the time of the translation plus the time of running the Bobilli subroutine. If we have a lower bound on Bandersnatch, then the lower bound minus the translation time is a lower bound to compute Bobilli. One of them is a technique for getting fast algorithms. One is a technique for saying there isn't going to be a fast algorithm. Any questions? So both ways it's good to think about. Okay. At one point in my life I tweeted, okay? This is the best tweet I ever made, okay? And I want you to think about how profound this is, okay? An NP completeness proof ensures that a dumb algorithm that is slow isn't a slow algorithm that is dumb, okay? That's what we are doing here. Why? What does this mean? What is an example of a slow algorithm that is dumb? If I give you a sort that runs an n factorial time, is that a slow algorithm that is dumb? Yes. Okay. Now, what is a dumb algorithm that is slow? Okay. That is something like searching through all possibilities, right? It's not rocket science to search through all possibilities. But if you have a problem where that is essentially the best possible algorithm, that is not dumb. Okay? Any questions about that? Okay, so that's the philosophy here about NP completeness and why it works. Any questions at this point? Yes?
I'd like to know if the translation is always bidirectional. Like if I can translate from problem G to P, can I translate to P to G?
Okay, the translation, what is the translation saying? I'm translating Bandersnatch, I guess if I write it out, Bandersnatch of G, I get translate into mobility of Y, okay? The only thing that I'm guaranteeing is the answer is going to be the same. It's not clear that I can go from a, I don't have to be able to take my translation and somehow run it backwards. I don't think I have to in any fundamental way. The important thing is that the answer has to be the same. Okay? That's the requirement that I'm looking for. Any questions? Okay? So if you think about that, again, back to the duality problem we had last time. The answer was either, yes, there is a point that is on 3 lines, or yes, there is a line that's on 3 points. Okay? And the answer has got to be the same. That's kind of what the important point is. Any questions? Okay, let's look at reductions. Okay, and again, I told you the reduction is translating one algorithm into another algorithm. It's sort of an argument that if I reduce problem A to problem B, it means that if I can solve problem B, I can solve problem A. Okay? That's kind of the important things. Now, many problems are reducible to sorting. Okay? If I know how to sort in n log n, I can solve a lot of problems in n log n. Okay? How do I solve whether all the elements in a set are distinct? Okay? Well, if I give you a set, are there any duplicates? Well, you sort it, and the two elements, once you've sorted it, it's easy to tell whether there's any duplicates. They're next to each other. So that's the idea of reduction, is you kind of turn it, the hard part, into another problem. Now, there's one last illustration of what the philosophy of a reduction is before we maybe get a little more detailed. There's this joke about this engineer and this computer scientist are sitting around and they want some tea. They're sitting around. And the engineer suddenly says, I want some tea. Okay? And he goes over to the shelf, pulls down a tea kettle, puts, I know you guys in Argentina seem to drink your tea differently, but where I come from, you put it in, you take a tea kettle, you put water in it, he puts it on the pot, on the fire, turns on the burner. The computer scientist is watching with great interest as he does this. Okay? Water boils, he takes some tea, puts it in the glass, okay, pours the water, okay, puts the tea kettle on the stove again. Okay? The computer scientist looks at this and then says a few minutes later, I want some tea. What does he do? He takes the set of the tea kettle with hot water in it, pours out all the hot water, okay, dries the kettle, puts it back on the shelf, and sits down. Why? He says, now I've reduced the problem to something that's already been solved. Does everybody see that? Because if you understand that, you understand what the idea of a reduction is. Okay? Any questions? Okay? Okay, good. And this, by the way, was generated by one of those AI image generators, which is kind of, I think, an amazing thing, by the way. Okay, good. Okay, so let's now talk about reductions again a little bit. And one set of slides when I was talking about graph algorithms that I didn't get to, that I had wanted to, was this idea of saying make graphs, not algorithms. One of my favorite algorithm design techniques, when you take graph algorithms, you learn a small number of classic problems. You learn about network flow. You learn about shortest path. You learn about minimum spanning tree. Okay? And when I give an algorithm problem in my class, I find it's very tricky to design a graph algorithm that is provably correct. What's often easier is if I can find a way to translate the input of the problem I have into one of the classic algorithm problems, so that solving the algorithm problem, the classic algorithm problem on the transformed graph is the right way to do it, will give you the right answer. So this is an algorithm design technique I like that's based on this philosophy of doing reductions. And so let's look at one example of a problem that conceivably might be on a programming contest, simple one. Suppose I am giving you a graph. The graph is weighted, okay? And I want to know, I want to know what is the shortest path from S to T using exactly k edges. Okay, does everyone see what the problem is? I go from S to T. I want to use the shortest travel time, but I don't like making turns when I get to an intersection. So I only want to make exactly k turns. How do you solve this problem? Anybody understand the problem? Okay, how do you solve it? Yeah. You say just Dijkstra on what is the key question? Is it just Dijkstra? The answer is no. Dijkstra will find you the shortest weighted path. Does everybody see that? What if I asked you to find the shortest path from S to T using the smallest number of edges? I just can't want the smallest number of edges. I don't care about how the weights on the edges. That's BFS. If I want to solve what is the shortest path in a weighted sense, that's Dijkstra. But what if I want some kind of an intermediate path? I want my path to be short in drive time, but I see the intersections that you guys have in Brazil. I don't want to make too many turns, okay? I'm willing to make k turns, okay? How do I find the shortest path from S to T under the restriction that I only can use k turns?
Copy your graph.
Okay, before I copy my graph, what's the simple thing that you're supposed to get? What's the way you're supposed to do this problem on a programming contest? You need to do it short. Does anybody, I thought everybody was going to scream dynamic programming. Okay? So let's first see, how do you do it with dynamic programming? Okay? My claim is that the shortest path from S to T using exactly k edges is going to be what? I'm going to make go from S to somebody, J, and then I'm going to finish the path from J to T using k minus 1 edges. Does everybody see that this dynamic program does this? Okay, so this is what I thought you were going to come up with all and say, yeah, that's the right way to do it in a programming contest. And probably the right way to do it overall. But we're thinking reduction. What is the way that you would do this if you're really burning to use your Dijkstra algorithm solution?
So you copy the graph k times, and the ith copy means I already have gone through I edges. Of course, the edges will have to change so that they go from the ith copy to the ith plus 1. And then we just want the path from the 0th copy to the kth copy.
So, okay, do people get that idea? That's kind of what I'm sort of trying to draw. I'm trying to steal something from the network, so it's not clear that this is not the right drawing probably. But philosophically, it's the right idea. I'm going to make k copies, okay, of where I am. For every edge in copy I, I'm going to have my edge directed to copy I plus 1, okay? The weight of it is going to be the weight of that edge. And then what do we know? The shortest path from S to T, using exactly k edges, is going to go to something, end up there. This is now shortest path. Okay, you can use your Dijkstra's algorithm on this problem. How many people see this reduction, why it's correct? How many people who don't see it and want to? Okay, that's good. What is the idea? Let's say I want to figure out What's the shortest path? Okay. What is the idea here? The idea here is, let me try one more time. There is an underlying graph here. What is the underlying graph in this drawing? Let's see if I can reconstruct it from the picture. What would that be? It looks like from 1, I can go to any vertice. If I have, it looks like I've got a graph that has 4 vertices on it, right? And from 1, I can go to 2, 3, and 4. From 2, I can go to what? 3 and 4. And from 3, I can go to 4. Does everybody see that's kind of the graph that's implicit in my drawing up there? If I want to know, can I go from 1 to 3 in a total of 1, 2, 3 hops? What's it going to be? I have made 3 copies of that graph where all the edges run from vertices I to vertices I plus 1. Now, any path of length k could be done by k edges on here, bop, 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 or it could be done by k edges on here, bop, bop, bop. Okay? That's the same thing. Okay? So I'm explicitly constructing my graph such that Dijkstra's algorithm will do it. Any questions? Actually, do I need Dijkstra's algorithm for this problem now? Why not?
Because there's
Because it's a DAG. Because it's a DAG. This is a DAG now, okay? Because all the edges are going forward. This is now a DAG. And now you can use your favorite dynamic programming problem solution to solve it on a DAG. Any questions about that? So this is the kind of thinking that I think is like, okay? I have turned this, instead of designing a special graph algorithm that works for where you're limiting the number of edges, I transform it into something I can use an implementation off the shelf. And this, I think, is a great way to think about the world. Any questions? Let's think about geometry a little bit, the relationship between convex hull and sorting. Okay? Now, convex hull are convex hull algorithms from yesterday, and the plane took how long? N log n. And what did they do? We basically sorted the points and then basically just did a little adjustment to it in linear time. Okay? So the reason why convex hull takes n log n is because it uses sorting. Okay? Now the fact that sorting has a lower bound of n log n, there's no faster way to sort than n log n. Is it possible that there is a faster way to do convex hull? No, why not?
Because you can sort using convex hull.
Well, okay, but wait, before that, but at least what you know right now, it could be that sorting was a dumb thing to do, okay? There may be a faster way to do sorting, to do convex hull, than the Gram-scan algorithm. I mean, Gram was one of those people who couldn't solve all those other problems, like Knuth and me, okay? Could there be a linear time algorithm to solve convex hull? Okay? That seems like a fair question, okay? I'm going to argue that we can't, that there is no fast way to solve convex hull. Why? I'm going to do a transformation. I'm going to do a reduction. What if I translate what if I show you a way to sort numbers using convex hull? What is Bandersnatch and Bobilli going to be in this world? Remember back to Bandersnatch and Bobilli? If I want to show you you can sort using convex hull, which is which? Which problem is Bandersnatch? Sorting. And which problem is Bobilli? convex hull. What if I map every point, if I'm sorting a bunch of numbers, x, I'm going to map them to the point x comma x squared. Okay? Why am I going to do that? That's my transformation. Does everybody agree you could write a fast program given a set of n numbers, produce n pairs of the form x, x squared? This I bet you could all do in linear time. Am I right? Okay? Good. Why am I sort of doing this? X squared is a parabola. What does that mean? That means that this is a convex curve, right? Which of the points, if I give you a bunch of positive numbers that and I take those points x, x squared, I'm creating a bunch of points. Which of those points are going to be inside the hull and not on the surface? None. They're all going to be on the surface because it's a convex curve. What does finding the convex hull mean? It means chunking it. Kabunk, kabunk, kabunk. Turning that into a polygon is going to end up sorting the points by their x-coordinate. Does everybody agree with that? So convex hull sort is going to do what? It takes your numbers, constructs these pairs, calls Gram-scan on it, okay? If you could have a linear time algorithm for doing convex hull, this would give you a linear time algorithm to sort. Does everybody agree with that? Is there a linear time algorithm to sort? No. So therefore, there is no linear time algorithm for convex hull. That's kind of the ideas that we're doing here. How many people see that? See where I'm going with this? Any questions about that? Okay. Any questions? Okay, good. And this is basically the same thing that I said before. Now, for a lot of algorithm problems, I claim that there is, in thinking about it, is often a good way to build these transformations. Again, this is now more programming contest E, okay? There is a famous algorithm problem, or an important algorithm problem called shortest common superstring. What is the shortest common superstring problem? I give you a bunch of strings. Those represent 5 strings, each from left to right on that thing. That's a bunch of 5 strings. And I ask you to build a string that contains every one of the strings on the left as a substring. And I'd like that string to be as short as possible. Can anybody give me a fast algorithm to construct a superstring of n strings? Okay? If I don't make it be short. Just concatenate them. Does everybody agree with that? If I just stuck them left to right next to each other, I've got a superstring. Is that something to brag about? Well, it's a superstring. But you might want to find the shortest one. Like in this case, it was abracadabra. Okay? Which may mean something to you guys. Okay? How do you find the shortest possible superstring? Okay? Okay? The first thing, any ideas how you might think about this? You're saying think of it as a traveling salesman problem. What is a traveling, how many people here know what the traveling salesman problem is? How many people don't is probably a better question. Don't be afraid. What is a traveling salesman problem? You've got a bunch of vertices, okay, in a graph. There's a certain distance between, let's say, every pair or some pairs. And you want to find the shortest tour that will visit every one of the vertices and get you back home, right? That is this traveling salesman problem. What do you know about the traveling salesman problem? It's NP complete, but it's a problem that you know about. How can you think of this problem here as a traveling salesman problem? Okay? when I think about trying to do that kind of a transformation, I'm going to ask myself, what are the vertices? What are the edges? And what are the weights going to be? Right? That's what, when I'm translating it, that's what I got to think. So, what are the vertices? What should I use as, what should the vertices of each node in my graph correspond to? What? The word. So there's going to be string 1, string 2, string 3, string 4, ... right? What is the edge going to correspond to? What was that? Concatenate? Well, concatenating them, what if my words were cata and, talk? Okay? What is there, what would be, what is the interesting, and I want to go, what is the interesting concatenation of this? Okay, it's not that I stick one after the other. It's that the maximum possible, the shortest possible word containing both of them is going to involve the longest overlap, right? So what if for every pair of words I find what the longest overlap is between them? Okay? So the difference between the edge from cata to talk is going to have an overlap of 2. Does everybody see that? Now, what do I want? If I have a graph, it's a directed graph, right? Cata followed by talk has a cost of what? I save 2. What if I have talk followed by cata? What's the best I can do? Concatenate them, right? So I get a savings of 0, right? What is my claim now? If I have every string is a vertex, and the cost is how much they overlap, okay? What is it that I want for my for my shortest common superstring? In this case, I want the maximum possible cost, okay, tour that will visit every one of the strings, right? A tour that visits every string is going to contain every string, right? I want the one where I save as much as possible by overlapping it with my predecessor. The maximum cost tour here would be the what I want. Okay, does everybody see how we turn this into something that looks like the traveling salesman problem? But you're saying, oh, it's a maximum. Skeena's maximizing it. My TSP solution wants to minimize it. How can I make this a minimum problem? I could make all the weights negative. You may say, oh, my minimum weight traveling salesman solver doesn't allow negative weights. Is there anything else I can do? I can add, okay, and make every add the biggest possible number to every edge, and then make it the biggest number minus the second, okay? Anyway, right, I could say that instead of saying I want to gain the most savings, if I want to pay the minimum cost, if I have a big number minus the cost of each edge as the weight of each edge, then the minimum cost tour is exactly going to be my shortest superstring. Okay? So you see how I've turned this problem from something weird into something that is, what you call it, a standard problem. You might have solvers, you might have experience. Any of you guys know fast algorithms for solving traveling salesmen? Yeah, you got your dynamic programming, some of you may know about a dynamic program that's like 2 to the n, okay? So you can use those tricks on this problem now, okay? Any questions about it? Okay? So we like this world of transforming problems from one problem to another. You like randomized algorithms. Is that so that you guys use something dirty like that in your program for an NP complete program? I thought that they usually, in my era, what was my era? Well, yeah, I'm used to these things being exactly. But bottom line, being able to see a problem as something else is a very useful skill.
He can also travel inside man fast.
Okay.
That's not really
Okay, any questions about that? Let me show you one other case that some of you, even if you're NP completeness experts, may not be familiar with. Remember the last class we were busy dealing with our duality and our find, is there a line that contained 3 points on it? And the best that you guys could come up with that we really trusted was n squared log n, as I remember. Okay? Turns out there is an n squared algorithm for that. Okay? And there's a way of doing a sweep line algorithm where you don't force the line to be straight. Something called topological sweep. Don't worry, it's not, it's more sophisticated. But it turns out if you do that, that will go over all the points without paying the cost of sorting. Okay, so there's a way of doing that in n squared time. But how do we know whether there's a better way, something faster than n squared? It turns out that there is a notion that people talk about called threesome hardness, which is a question of, suppose I give you n integers in n integers, okay, which are not integers, positive and negative in numbers. So in integers, it can be positive and or negative. And I ask you, do they contain 3 values? Are there 3 integers in the set that add up to 0? Okay? How would you solve that problem, given a set of integers? What was it? -3, 7, 36, ... How would you give me an algorithm if I give you n of those? Give me a way to tell whether or not 3 of them add up to 0. Yeah.
Numbers, and then see the remaining number is also there, like making a 2-pointers algorithm.
Okay, so what I think I'm hearing you say is you construct a table. But no, actually, I'm not sure I hear what you're saying. You're going to say you're going to take the n numbers, I think, and sort them. This is what I think you're going to be doing now. You're going to sort the n numbers. So in n log n time, you have the n numbers sorted. Now you're going to consider you're going to construct all possible pairs of these numbers, right? And actually, I'm not seeing that right now. Choose one of the numbers. Yes. Okay, but that requires both tables be sorted. Okay, say this again. So which one? So we sort the n elements. Yeah. Okay, so you're going to say I'm going to take this number out, which was, let's say, going to be -7. And now you're going to ask me, are there 2 numbers here that add up to 7? If this number is too big, bigger than 7, it can't possibly be there. Okay? So so the claim would then be you use 2 pointers and get that. Okay, I believe that. Okay? Any questions? Okay, but the question is there a faster algorithm? Okay? I'm going to argue that this is a problem that's pretty simple. People have thought about it. No one has a faster algorithm than n squared. Many other problems have been translated to this. One of them is do 3 lines in a plane meet in a single point. Okay? What does that mean? Which is my Bandersnatch and mobility? If I want to prove that do 3 lines meet in a point, if I want to see if it's hard, is that Bandersnatch or mobility? what do I want to do? So let's say, what do I know? I know that 3n, okay, is what do I know? I know 3-sum is a hard problem. No one knows how to do it better than n squared. What if I came up with a transformation such that my 3 points on a line? Suppose I could use, I told you I had a fast 3n points on a line solver that was faster than, ran in better than n squared time. There is a translation from this 3-sum problem to my 3n points on a line problem, okay? Such that if I could do this fast, I could do this better than n squared. But since no one knows a way to do this better than n squared, okay? So in fact, there's no reason to expect that anybody in the world can solve this problem faster.
The 3-sum problem. That's what it says there.
Okay, what it says there, let's say if I don't, okay,
This 3-line intersection can be reduced to 3-sum.
okay, what is the direction that I want this to go? 3-sum is the problem that everybody knows can't be done faster than n squared. If you did this, you would be famous. Well, I mean, to some level of famous. You solve traveling salesman faster than in polynomial time, you're going to be famous. Okay? Here, you're certainly going to shock the hell out of everybody. Okay? Now, what am I saying? I'm giving you an algorithm for doing this, solving this, using this 3 points on a line problem. If I could solve this one faster, then that would mean I could solve 3-sum faster. Since no one knows how to solve 3-sum faster, I'm telling you that no one knows how to solve this one faster. That part of the reasoning is right. I'm not going to read my slides. The slides are for you to read, not me. Okay, but this is what I think I want it to mean. Any questions? Okay, so this is kind of interesting. Okay, any questions? Okay, let's see what I go on here. Do people understand this now? Do people understand this Bandersnatch-Bobilli idea? Okay, what this transformation means now? Okay, I'm translating my Bandersnatch, my problem instance, into an instance of another problem, calling a subroutine on that other problem, where the translation was done carefully enough that the answer of Bobilli of y is the same as Bandersnatch of g. If I can do this translation, it means one of two things. Either a fast Bobilli solver gives me a fast Bandersnatch solver, or a proof that there is no fast Bandersnatch, because everyone in the world has tried to find it and failed. Okay? Suggests that there's no fast Bobilli. That's the idea here. Any questions? I think people get it here. I usually have to repeat this many times. So let's look at a bunch of different graph algorithms. You guys like graph algorithms. It turns out that there is a large number of famous graph algorithms that are NP complete. Okay, and I'd want to go through some of them just because I think it's good to know when you recognize when you see an NP complete problem. Okay? One problem that's NP complete is vertex cover. How many people have seen vertex cover on some level? Okay? Given a graph, find a smallest number of vertices such that every edge kisses or is incident on at least one of the vertices in the cover. So for this graph, 2 vertices in the cover suffice. Okay? How hard is that? NP complete. We'll talk about that in a minute. That's something I should have gotten rid of. Now, when you're trying to transform problems, NP completeness is about trying to transform one problem into another problem. Okay? and it's easier to translate a problem that is that looks similar to it. Okay? So what other problems are there that you guys know that kind of look similar to vertex cover? At least if you look at it in the right way. What about maximum independent set? Okay? What is maximum independent set? In this case, I am given a graph G, okay, and I want to know, excuse me a second, I don't know what happened. I am given a graph G, and I'd like to partition, okay, I'd like to find a subset of vertices of the graph such that no two, okay, independent set. I'm given a graph. I want to find a subset of vertices such that no pair of vertices in the subset have an edge between them. That's what it means. Given a graph, can anyone give me a fast algorithm to find an independent set on that in that graph? Take a random vertex. Does everybody see that? Okay. Should we be impressed? No. Why? Because where we should be impressed is finding the largest such subset. I don't quite know where my voice went, but somewhere. Okay, let's try one more time. So, given a graph that is a grid, does everybody see that there's a way to take the checkerboard and make half the vertices, pick half the vertices, such that there is no edge between them, right? That's what you see here on the checkerboard, right? So either the red or the blue vertices cover half the set, and there's no edge between red and blue, okay? Or between, no, take it back. There's no edge between blue and blue or red and red, okay? What is the connection between vertex cover and independent set? Well, let's think about it first. Let me just think. I'm just trying to think cosmically, and then I'm going to ask you this question. Both of them are graph problems. One of them, vertex cover, says I want the most vertices such that every edge is covered, right? No, I want the smallest number of vertices such that every edge is covered. It's a minimum vertex cover. For maximum independent set, what do I want? I want the maximum number of edges, of vertices, such that no edge is covered. Does everybody see no edges hit twice? Okay? So the problems, do they smell the same? Maybe, maybe not. It depends what your sense of smell is. But are they the same? What makes these problems the same?
If you take the complement of one.
If I took graph G and I took the complement.
No, just the same graph. You take the nodes.
Oh, okay. So you're telling me if I have a, go ahead and tell.
Maximum vertex cover, a minimum vertex cover, and you want a maximum dependent set, you take just the nodes that aren't in the minimum.
So take a look at this example here. Sorry, oops, boop. Here, what is my vertex cover? Does everybody agree on this vertex cover? Only two vertices will suffice for covering them, right? What is the largest independent set in this graph? What? All of these, if I take all of these vertices, does everybody agree that that is an independent set? Right? If you have a small vertex, if you have a small vertex cover, the claim is that everything that is not in that vertex cover is an independent set.
Yes.
Why is that have to be true?
Because you have two nodes in your supposed independent set that are connected, then that edge wasn't covered in
Right.
vertex cover. So
Suppose there was some edge that went between two vertices that were not in the cover. What would be the problem? You didn't have a cover, right? So the smaller, any vertex cover, the vertices not in that cover are an independent set. If you have the smallest vertex cover, it leaves the biggest independent set. So which is harder, to find a large independent set or a small vertex cover? They are exactly the same problem. I can get you guys maybe getting into the same debate I had you do with the duality thing about 3 points on a line or 3 lines on a point. Okay? If you can find a small cover, you can find a large independent set. What does that mean in Bobilly Bandersnatch world? What? Turns out that I have both directions, but what am I saying? To solve vertex cover of G, I guess what I was doing there was solving maximum independent set of G. This was the argument we were doing, although it will work both ways. What were we going to do? We were going to call vertex cover on G, and we were going to take, basically return, take the numbers 1 through n, the vertex numbers. The set of vertices minus the vertex cover. I think that's kind of what my algorithm is, right? Complete set of vertices minus the vertex cover. Gives you, if you have a fast vertex cover solver, this gives you a fast independent set solver. I could, I believe, just rewrite this. Okay? If you have a fast maximum independent set solver, you have a fast vertex cover solver. Does everybody see that? These two problems are as hard as or equivalent to each other. Okay? I haven't proven that either of them is hard, but I've proven them that they're the same. And that's kind of what I talked about here. One last problem before you get your coffee, okay? There's a problem here called maximum clique, okay? And again, I don't know if life in Brazilian high schools is different than life in the American high schools. But in, suppose, let's say, I seem to remember in high school, you had groups of friends who were very, very tight, who would hang together and you know, piss off everybody else, okay? This was called a clique, a clique in my high school. Suppose, let's say, we have a graph, which is a something like Instagram or whatever you guys use, a friendship graph, where between any two people we say which pair of you are friends, okay? Now, a clique, okay, or maybe I guess Taylor Swift may call it a posse, or I don't know what this world is these days, okay? A set of people who all are friends with each other. How do you find the largest group of people who are mutually friends with each other? Every person is a friend with every other person in this group. Such a thing we call a clique. Can anybody give me an algorithm, given the friendship graph, to find me a clique?
A click.
Yeah, what are you going to tell me?
Take a random vertex.
Take a random person. You can imagine you walk through high school as a clique of one, okay? That's true, okay? What? Or you could take an edge, you and your friend. That's maybe a slightly brighter view of the world, right? That those two, every pair of you are this thing. But consider the problem of maximum clique is to find the largest set of vertices such that everyone is a friend of everyone else. Okay? This problem Does it smell like any other graph problem that you have seen? Okay, which of our problems here does this smell like? You say it smells like maximum independent set. Why does it smell like maximum independent set?
And just solve max independent set on that graph.
So what is the maximum independent set here? Here, let's go back to our thing. What is this maximum independent set? These were a set of people who had no two of which were friends, right? If I knew a way to solve that, is there a way that I can solve clique? Let's go back to this one more time. Clique. Find the biggest clique on a graph of size G. How do I do it using my maximum independent set solver? What do I have to do?
Every edge, sorry, that's in the graph, take it off.
I have to complement the graph.
Yeah.
How do you complement the graph? Say nice graph, right? Okay? Or you can say, let's say G prime is going to be equal to G complement. Basically, if this was my original graph, my complement is going to be a graph which has an edge wherever there was not an edge, okay? And does not have an edge in the original. What does that mean? A clique in G is going to be an independent set in G prime. Okay? Does everybody kind of see that? So all three of these problems are kind of, in some sense, equally hard. You could solve any one of them, and you get all three of them. Okay? But if you don't know how to solve any one of them, you don't know how to solve any three of them. That's kind of the interesting point here. Okay? Any questions about that? Actually, I lied when I said I was going to send you away to coffee break quickly. Let me just ask one quick question. Here is a slightly more challenging problem. Let's see if any of you can prove to me that this problem is hard. What about the problem of finding the densest subgraph in a graph? I give you a graph, and I give you an integers k and y. And I ask, does the graph contain a set of k vertices which have at least y edges between them? Is this problem hard? Do you see that if y is equal to k choose 2, this is another way of asking for a clique, right? Is this problem harder than clique or easier than clique? This problem has to be at least as hard as clique. Why? Because if you call it for y squared, for y equals k choose 2, it's a clique solver. If you call it for other things, it might be another solver. This proves that densest subgraph is at least as hard as clique, but it might be even harder. It can do all kinds of other things, maybe, but actually probably not. Okay? Any questions about that? You see how you're transforming these problems? Okay, this is good for the soul, as is a coffee break. So have your coffee break, and we'll get back and finish this. Start it again and get back to NP completeness world. Okay. Any questions so far about, we've been starting to talk about these reductions. I think I've shown you that there is this interesting transformations between one problem and another problem if you learn to look at it the right way. And so when I think of things like NP completeness, I think about it as in terms of how easy, how to see that two problems are the same thing. And this I find very, very satisfying to think about. Okay, any questions about what we've covered so far or anything like that? Okay, what I'd like to talk about now, just as for my next little section, is just give you a little gallery of NP complete problems that you should know about, that you know that you should know. I find it's very useful to know the names of problems, just because it gives you a way to talk about it. It gives you a way to think about what the problem should be in its pure form. Okay? And so what is the most famous? What is the mother of all NP complete problems? It is something called satisfiability. It's a logic problem. How many people here know what satisfiability is? Okay, how many people don't? Okay? Basically, just to give it quickly, I give you a logic formula. Okay, I give you a set of clauses of the form a variable or its negation. And I make a bunch of logic of clauses of the form x1 or x2 or not x3. Is there any way to make the equation x1 or x2 or not x3? Is there any way to make it true? How do you make it true? Just that one clause. x1, if I give you x2 or not x3. Is there a way to make it true?
Yes, there are many.
Sure, there are many. How many?
Okay. Well, at first you can choose true or false, but you need a true on each, at least on each one of them, so you count.
I need a true on at least one of the three ways of doing it, right? So how many is, if I just have the special formula, one clause, very simple, x1 or x2 or not x3. How many ways are there to make this true? 7. There's 8 ways to flip the bits. And unless I flip the bit false, false, true, that formula will be true. So if I give you one formula and I say make it true, this is no problem, right? What? The problem is, here I've got a bunch of logic formulas all on the same set of variables. And I'm going to ask, is there a way to make all of these things true? Okay? The formulas are of the form variables or, or the or of a bunch of variables and possibly their negations. And I'm giving you a bunch of these formulas. We call each formula a clause. Okay? And the question is there a way to make it true? That's what the satisfiability problem says. Given a logic formula, is there a way to make it true? What?
Right.
Well, make them all true. So it's a way to think of this. This formula is really kind of this clause and this clause and this clause and this clause. So the ands make it all true, right? This is an and formula of a bunch of or formulas, right? There's probably a name for that. I think I don't know if it's CMF or something like that, okay? And the question is there a way to make it true? You could imagine you tell some story to your parents about your behavior on a night, okay? And you then want to see, hopefully, if they start challenging you on this, you hope there is some way to make what you said true, right? You're trying to solve a satisfiability problem. Does everybody see that? Okay? And for some formulas, you can satisfy it. For some formulas, you can't. if I have the clauses V1 or V2, and V1 or not V2, and not V1, is there a way to make that true? Okay? To make the last thing true, V1's got to be false, right? If V1 is false, I can make the last part true. Is there a way to make, if V1 is false, is there any way to save the second clause? Yes, by doing what?
False.
V2 is false. But if V1 and V2 are false, I'm screwed on the first clause. Does everybody see that? There's no way to make that with this thing true. Some formulas you can make true, some formulas you can't. To decide whether that's true is the satisfiability problem. And this is the mother of all NP-complete problems. When the first part, when Karp and Cook started talking about NP-completeness, they said, the hardest problem in the world is the satisfiability problem. They can prove that every other problem in a big class of problems, if you could solve satisfiability, you could solve all of them. Okay? So this puts a big target on the back of the satisfiability problem. If any of you can prove satisfiability is polynomial, give me a fast algorithm for satisfiability. You would give a fast algorithm for every other problem in this big class of problems we call NP. Details not to be discussed yet. Okay, and maybe not to be discussed. Okay? So this is the mother of all hard problems. This is the one that everybody has gunned for. Okay? So remember we had the slide at the beginning where we saw Corman and Knuth and Skeena in the line confessing they cannot solve your problem. They have, we all confess we cannot solve satisfiability. Once you prove to me your problem is as hard as satisfiability, we are helpless. Okay? And that is the power of NP completeness here. This is the mother of all the hard problems. Any questions? Okay, good. What other NP-complete problems should you know? Okay? One problem of my favorite NP-complete problems is the integer partition or subset sum problem. I give you a bunch of integers, and I give you a set of integers, and I give you a target. And I ask, is there a subset of your set that sums up to exactly that target? Okay? Now, so for example, in this case, I gave you a bunch of integers. I give you the target was 3754. In this case, there is a subset that adds up exactly to that problem. Okay? This problem is called subset sum. Integer partition is given a bunch of numbers. Is there a way to break that set into two sets such that the sum of this set equals the sum of that set? Okay? Both of these are hard problems. Okay? Any questions about the integer partition problem? Does this look familiar to you, this integer partition problem? When did you see this integer partition problem? Last night or yesterday? Problem, what was it? A. What was your problem A? That was the one with the drunken walk that he had on the board? What was that? He said that he had, I guess you were starting at one point, and you had to find a way to, he was taking steps of a certain size, and you could either go forward or backwards, right? And you had to find, is there a way to label every step such that you get back home? That's basically what the problem was. Am I correct? How does this compare to your problem? Let's think about it. Your problem, you had a bunch of things and you were comparing how hard is it to get near home. Now, when I think about it, what's the nearest you can get to home? At home, right? This is problem is saying, what is the subset sum problem? Or the integer partition problem is the easier way to look at it. Suppose I have, let's say that this guy lived on, it's funny, let's say they lived on Paulista Avenue in San Paulo. Is that, do people know about that? Or, okay. And all they do is drunkenly, they walk certain length, they can either go up or down San Paulista Avenue. You have their set of potential steps, right? And you have to decide, is there a way you could have gone up or down on each step? This is a one-dimensional version of your problem, right? Is there a way to assign for everyone, said the guy's going to take a, oh, I'm drunk, I don't know, I'm going to go walk 5 steps, should I go left or right? Is there a way to tell them left or right on every move to get back home? Does everybody see this is exactly the integer partition problems? Is there a way to make it so the sum of my steps going left is equal to my sum of my steps going right? Okay? This problem is NP complete. Okay? So when you see it that way, I know your problem is somehow an NP complete problem. You're saying, wait, we did it in 2 dimensions. Does 2 dimensions make it any easier? Well, it doesn't make it any easier. You could always set the second dimension equal to 0. And then this problem is exactly this, right? Any questions about that? You see how recognizing it as a hard problem, you know, this kind of thing, once you've seen these problems enough, hopefully you can recognize that instantly. It changes the way you think about it. Okay? Actually, I got a question for you. So everyone knows about the subset sum problem. You guys are, well, subset sum problem was, again, let's just say we have the problem of I give you a bunch of integers, and I give you a target, and I say, is there a subset of the numbers that add up to here? That adds up to this target. That's my subset sum problem. Now, I'm telling you this is NP complete. NP complete means there's no fast algorithm known for this. Do any of you know a fast algorithm for this problem?
Dynamic programming.
You're saying dynamic programming. Let's just remember what the problem was. Here we have a set of integers. We have a target. Does there exist a, what you call it, a subset of those numbers that adds up to the target, right? How do you do that problem with dynamic programming? Have people seen this before in dynamic programming? Wave your hand if you did. Okay. So what was the dynamic program? Let me see if I can reconstruct this from memory. But I think it's a question of I'm going to want M of I, J to be equal to true if the sum, if there exists a way for the first to find a subset of the first of numbers 1 through I that adds up to J. This is the way I think I'm going to do it, right? So I'm going to ask myself, here are my set of numbers, dot, 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 dot. I'm going to consider the first I of them. Is there a way, is there a way that this subset adds up to J? I'm going to claim that this is true if it's going to be what? This is going to be equal to true. What is the recurrence? I believe it is M of Ij is equal to M of I minus, oh no, J, wait, I minus 1. What's my target going to be? J minus the number, the ith number, or M of I minus 1 J. This is my dynamic programming recurrence for this. Is this a fast algorithm? What is the running time here? Okay, so anyone looks fast to me. What is the running time of this algorithm? There's n choices for the first one, Jay. This is going to be n times t. Now, is this a fast algorithm for it? Have we just solved satisfiability quickly? No, and the reason it's not is a tricky thing. It looks polynomial to me, but it's polynomial in the value of the numbers, not the number of the numbers, okay? If these numbers were numbers represented the height of something, the distance in, let's say, kilometers, right? Or, no, let's say they measured the distance in, let's say, kilometers. If I converted those numbers to meters, all the numbers would get what? 1,000 times bigger, right? Did the problem get 1,000 times harder? By your algorithm here, it got 1,000 times harder, right? In terms of, let's say, how we normally think about things, it didn't get harder. You kind of see that? If I convert it to millimeters, does it now become harder? Now it's, I guess, 1,000 times, maybe another 1,000 times, 1,000,000 times harder. Okay? This is exponential. This is linear in the size of the number, but the number can be exponential in the size of the number of points. That's kind of what the issue here is. Okay? So for small numbers, this is a good algorithm. For big algorithms, numbers, this is toast. Does everybody see that? And do everybody see that the problem, if you multiply all the weights by and target by huge numbers, that will make this algorithm terrible, even though it's really the same thing. Okay, this is why this is not a fast algorithm for satisfiability. Any questions about that? Okay, that's useful. That's a useful thing to be able to understand. Okay, any questions?
Reduction from satisfiability to subset sums.
What is the okay, so now the question is, what am I saying? I'm telling you, satisfiability is the mother of all problems, okay? Subset sum is a problem. How do I transform subset satisfiability, which is a logic problem, into a, into this integer problem? What I will tell you, if you look at my algorithms book, I will show you how you transform satisfiability into vertex cover. Okay? And that's kind of cool. It would take longer than I think I want, unless you guys want to give up lunch. Okay? And I show you how to turn vertex cover into subset sum. Okay? So I know there's a direct way to do it, but it'd be probably pretty messy. But if you look at the two things in my book there, I understand them. So you guys could understand them if you read them enough. Any question? And actually doing those kind of transformations I find very, very cool, because you're translating something that looks completely different than each other. How can numbers be the same as a graph? Okay? But in fact, there's a logical way to do that. That's complicated in the way that, that it's very intricate, and you said, my God, that's a crazy way to do it. But it's a logical transformation once you see it, okay? And that's why I love these NP completeness proofs. Any questions? Okay, good. At some point when we were talking about network flow, we had some OR people sitting back here. They were proud that they could solve linear programs. There's efficient ways to solve linear programs where you've got constraints. Is some linear combination of this less than some value? And you had a maximization criteria. And the question was, is there a way what is the maximum value you can get for this formula by values satisfying that constraint? For linear programming, where you're allowed those things to be numbers, there's a fast algorithm. If you insist that all the variables be integers, okay, this problem becomes integer programming, and it's NP complete. Can anybody see any of the problems we've talked about that's integer programming, that smells like integer programming, that's NP complete? Is there any problem we've seen here? What?
Satisfiability.
Satisfiability. What is satisfiability saying? Is there a way to make first of all, what is satisfiability? Satisfiability is operating on logic variables, right? Logic variables are true, false, or 0, 1. How in an integer programming problem can I force variable x to be equal to 0 or 1? If I say x is greater than or equal to 0 and x is less than or equal to 1, if x is an integer, suddenly it's a lot like a logic variable, kabunk, kabunk. Now if I have one of these logic formulas, x1 or x2 or not x2, how do I make that into an integer constraint? What?
You can transform the OR.
You're sort of saying, is there a way that I can make some other variable such that x1 plus x2 plus not x3? So one possibility might be to make it 1 minus x3. What if I say that a variable of x bar is equal to, what if I said that x bar is also between 0 and 1, and I said that x plus x bar is equal to 1? Does everybody say that if I say x plus x bar is equal to 1, what's that saying to me? Saying exactly one of them is going to be equal to 1, right? So I can make that like a summing thing here, right? So now I think if you're listening to me, you're starting to see how this smells like satisfiability, right? And before I want to maximize this thing, what is my maximization going to be? Well, I want any combination which satisfies all of them. So I don't really care too much about what my maximization is. Maybe I'll say I'll max x1. That way, by integer programming, you'd give me a solution with x1 set 1, if you could, but if you can't, you'll give me one where it's going to be set to be 0, right? So this should smell, see how when you start to think about these problems, you start thinking about problems and how they turn into each other. And that, I claim, is a useful skill to have. What's another problem that's hard? Okay? Given a graph, what is the largest number of edges? Can you find a way to split the vertices into 2 parts such that you got the maximum number of edges? Okay? This is called max cut. And again, if the graph is bipartite, how do you find the max cut? This is pretty easy, right? Every edge has to go from left to right. You put the 2 sides separately, ka-chunk, with one axe swing. You cut all the edges, right? But in general, this is not so hard. And wait a second, he said something about max flow. Max flow in cuts finds the best cut. What cut does the max flow find? The smallest cut. If you want to find the biggest cut, you're out of luck, okay, because it's NP complete. Any questions about that? Okay? So recognizing when you've got a problem like this is a useful thing to be able to do. Another problem that's hard is vertex coloring. Given a graph, how do you color the vertices such that any pair of vertices that are neighbors get different colors? Given a graph, how do you find a coloring, a legal coloring of that graph?
You can use
If you have a big enough set of crayons, you can color every vertex a different color. But if you want the smallest number of colors, that is a minimum coloring problem, right? What graphs can be colored with one color? What? The empty graph, just where you have vertices and no edges, right? What graphs can be colored with two colors? Bipartite, and all you guys say, if I do my breadth first search, I can tell if a graph is bipartite. I can two-color a graph. Once you have three colors on a graph, NP complete. There's no fast algorithm to color a graph with three colors. Okay? That's what happens with a lot of these problems, is they suddenly become hard when you go from 2 to 3. That's the big jump. Okay? Any questions about that? What about edge coloring? Okay, I give you a graph, and I want you to color every edge such that no edges of the same color kiss each other. Okay? What does this smell like? Have you ever done anything like that? If you think about it, the best what?
It sounds a bit like satisfiability.
Saying it sounds like satisfiability to you? It doesn't sound like that to me, but maybe that's fair. Okay? It sounds a little bit like matching. What does matching do? Remember we did by matching in a graph? What was a matching in a graph? It was a set of edges that you could color the same color because no two of those edges were going to be done, right? So you might think of this as being, how do I take the edges of the graph and break them into things like matchings? What's the smallest number of matchings that will completely cover the graph? That's kind of what this thing is asking for, right? For finding one matching, that was easy. We talked about it. But in this case, the problem is NP complete, to find the smallest. On one of my other slides, I had a beautiful picture of showing you how you could break the complete graph into disjoint matchings. That was an edge coloring of this. Any questions about that? What do we know about the degree? Suppose I have a vertex of the degree k. What do I know about the degree of a vertex and the edge coloring? It's a lower bound. If I have a vertex of degree k, is there any way I can color this vertex? I color the edges where no two of these vertices used more. So if I count the largest degree, that is going to be a lower bound on the size of the optimal edge coloring. Turns out there's a kind of an amazing relationship that every graph can be colored in either the size of its largest degree, edge colored in the size of its largest degree, or the largest degree plus 1. And to decide which of those is true is NP complete. Okay? It's easy to take a graph and edge color it with the number of maximum degree plus 1. But if you want to say, can I get rid of one color? That problem becomes NP complete. Any questions about it? So there's this wonderful world of NP complete problems here. You know about graph isomorphism. Graph isomorphism is the problem if I give you two graphs and I ask you whether they are the same thing. Okay? Is there a way to relabel it? Okay? If I have a graph like, let's just make sure we're agreeing with this. If I give you a graph that, let's say, looks like this, and I give you a graph that looks like this, are these the same graph? Okay. How can you tell when I give you something like this? Are they the same graph? Okay? Yes, these are the same graph. I think everybody sees this, right? Can anyone give me an algorithm for testing whether one graph and the other graph are the same thing? What? Well, okay, if they have the same number of vertices and edges, if they don't have the same number of vertices and edges, they're certainly not the same graph. But are all vertices with the same number of vertices and edges the same graph? What if I had a graph that looked like, I'm going to say this. Don't shoot me yet. This is a multigraph, let's say. Let's say I'm allowed to have a multigraph. Does everybody agree this has the same, actually this doesn't have, this has 1, 2, 3, 4, 5 edges. This thing has 5 vertices. Is this the same as the other two? No, it's not. How would you tell whether one of these, if I give you 2 graphs, whether they are the same? Can anyone give me a procedure for doing this?
Next permutation.
Next permutation, that's exactly right. If you try all possible permutations of this, and then test whether the graphs are identical, okay, then that will test whether or not the graph is isomorphic. Okay? People get that idea? Now, is graph isomorphism NP complete? Turns out that graph isomorphism is in a weird state. There's no fast algorithm known, but it's also not known to be NP complete. It's kind of probably somewhere in between. Okay? Does that help you on the programming contest? No, you go through all permutations because we have no fast way to do it. Okay? Any questions about that? Okay, so there are a lot of these problems that are hard. Here's one that's kind of maybe you don't know about, or maybe you do. You guys know about minimum spanning tree, right? What is minimum spanning tree? Minimum spanning tree is you take a graph, you have weights on the edges, and you want to know what is the lowest weight tree that connects all the vertices in the graph. Does everybody agree with that? If I ask you to compute a minimum spanning tree, you guys are not intimidated by that, are you? Prim's algorithm, Kruskal's algorithm. What if I give you a graph and I then specify a subset of the vertices? So meaning this, I give you a big complicated graph and I then give you a smaller set of vertices from that graph. And I ask you, what's the smallest tree that connects just those vertices? You're allowed to use other vertices in the graph, but you don't have to use those other vertices in the graph. Does everybody kind of get that idea? Let's just say this one more time, because it's kind of surprising. Okay? Suppose I give you a graph, kabunk, 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 and I make edges here. Let's even leave an unweighted version, because that's going to be hard enough. If I ask you for the smallest graph that can connect all those vertices, that would be a spanning tree, right? Breadth first search, depth first search. What if I ask you for the smallest graph that connects this vertex, subgraph that connects from this vertex to this vertex? That's BFS. That's the shortest path, the minimum number of hops. But what if I tell you you have to contain some vertices? You're allowed to use others, but you don't have to use others. Find me the smallest tree that connects those. Okay? This problem is hard. This you may find surprising. You're saying, why can't I just build this minimum spanning tree and delete the stuff that isn't being used? You can do that. It's going to be a tree that connects the rest, but it's not necessarily the smallest one. Finding the smallest tree is NP complete. Any questions about that? Oof. What if I take a graph and it's a direct, I want to take a graph and break every cycle in the graph. Let's say I give you a graph. It's an undirected graph. And I want to now know the graph has n vertices and m edges. Suppose I want to delete it, vertex edges, so that there's no cycles in the graph anymore. Can anybody give me a way to take a graph, to delete edges, such that there are no cycles left? Delete all the edges. That's good. Okay? Are we impressed? We want the minimum such set. What's the smallest number of edges we need to delete to break any cycles? Well, okay, for for an undirected graph, this is just a spanning tree, right? You take the spanning tree, okay, it has no cycles, right? What happens if you add any edge to a spanning tree? Does it have a cycle? So if it's an undirected graph, to break all the cycles, what do? You take you find a spanning tree doing DFS or BFS or your ever favorite spanning tree algorithm, and delete everything else. But what if it's a directed graph? If I have directed cycles, if everybody see, here I've got a graph that has all those edges. If I want to break those cycles with the smallest number of edges to cut, what do? If I cut the ones with the red, those 3 edges, every directed cycle on that graph is going to break. Okay? How do I find the smallest number of edges that if I delete them, the graph is disconnected? Or the graph doesn't have any cycles? That is what we call feedback arc set. And that is NP complete. Okay? So this is something else you can't do. Okay? But recognizing that you've got a problem like that is a useful thing to know. Any other questions? What if I give you a collection of subsets, okay? And I ask myself, find a collection of subsets such that, maybe like you guys form cliques or you guys form groups, right? You guys are programming teams, right? And some of you are at the same school, so you're friends in other ways. What if I took all the subsets of groups here? What is the smallest number of groups I need to have so that everybody is represented? Okay? Does everybody see this situation? Each group here is a subset. Set cover asks, is there a bunch of elements? Is there a collection of subsets such that every element is included in at least one in my collection? How do I find a set cover? What? Take all of the groups, right? But what if I only want to talk to a small number of groups? Finding the smallest number of prescribed groups, okay, that covers the graph is NP complete. No fast way to do it. Which NP complete problem that we already know about does this smell like? Vertex cover. What is vertex cover asking? Is there a set, find me a set of vertices such that every edge is included, right? The subsets are of size 2, the edges. So this problem is clearly related to vertex cover. I think vertex cover is clearly a special case of set cover. So what does that mean? If you could solve vertex cover quickly, you could solve set cover quickly, right? Can you solve vertex cover quickly? No, so set cover is also hard. Okay, I mean, anyway, the reduction, if you do it the right direction, I'm not sure, speaking loudly, I said it the right direction. But you should smell that those two problems are the same. One is a special case of it. If it's if the special case is hard, the problem is hard. Let's just keep going. What other ones are hard? Suppose I give you a set of items. Okay, you want to move from Rio to San Paulo. Okay, you have a truck. You have your stuff. You want to pack your stuff in the truck. Can you pack your stuff in the truck? This problem is bin packing. The shape of the truck is that rectangle over here. Is there a way to arrange your boxes so it fits in the truck? This problem is hard, okay? Does it smell like any one of the other problems we had? This smells like integer partition, or that smells, okay, what does integer partition smell like? Suppose your truck was, I guess if you had a truck with the property that it was 2 integers wide. Suppose I gave you a bunch of integers. I can make everything integer into a box. That's I times 1. Everybody see that? I've got boxes that are width 1. If I give you a truck that's width 2 by the shape, by half the sum of the integers, the only way that you can pack this truck is by declaring the ones that you're going to call positive are going to go on one side, and the ones that you call negative are going to go on the other side. Trying to find the best way to pack the truck is the same as integer partition. It's as hard or harder than integer partition. Any questions about that? Again, there's this world of seeing that different problems are the same thing. And that's the world that I like to live in. Any questions about that? Okay. Let me just do something else. I'm not going to tell you my secrets for proving hard problems hard, just because it's a little bit more intricate than we want to go, but I encourage you to read my algorithms book. People have heard about this P versus NP problem, right? Do people know what P and NP are? Okay? P is the set of problems for which there is a fast algorithm, the algorithm that can be solved in polynomial time. Okay? If you have, shortest path is in P. Sorting is in P. Convex hull is in P. NP is a set of problems that you can check the answer if somebody tells it to you in polynomial time. If someone gives you a traveling salesman tour of a graph and tells you this is of weight less than or equal to 7, can you check? You add up the weights on the tour. Huh, he's right. How did he find the tour? I don't know. Okay? If you can just test it, we say it's in NP. If you can check it, if you can compute it, it's in P. So NP is a set of bigger problems. Usually for any problem, if I give you a fast algorithm, can you check whether the answer is right? Yes, solve it yourself and see if you get the same thing. Okay? So NP is a set of problems where you can, if you guess the answer, you can check whether you're right. Okay, efficiently. And what the distinction of NP complete is basically that a problem is NP complete is if it is as hard as every single problem in NP. Okay? And the amazing proof that made satisfiability impressive is they show that every possible problem in NP, if you can solve satisfiability quickly, you could solve any of those quickly. Okay? That's why satisfiability is the mother of all hard problems. Okay? Does that mean satisfiability can't be solved quickly? Not by itself, but given the fact that people have tried to do this for a lot of things and they can't do it, it's damn good evidence. Okay? Any questions about P versus NP or anything like that, or anything like that people might be interested in? RP, is P equal to NP? Well, there's a recent result actually on this, okay? If you notice, P is equal to NP if N equals 1 or P equals 0. Anybody get that? Okay. Okay, this of course is meaningless, okay, but kind of cute. Okay? So, but, so no one knows for sure whether P is equal to NP. I am betting the answer is not. I am certainly living my life as though the answer is not. Okay? So once I know that a problem is NP complete, I know that we are in good shape there. Any other questions about this type of stuff? Yeah.
Given an answer, I can check in polynomial time if it's correct.
Yeah.
How do you classify it?
If I have a problem that I can check in polynomial time, then it's an NP. And you're saying, wait.
I want to check if this answer is correct.
Okay. Okay, so the question is, how do I check whether an answer is correct? And there's something a little subtle in what you're saying. Okay, so let's think about this. If I ask you, if I give you a graph, and somebody says, here's the traveling salesman tour. This is the best possible tour on this graph. Can you check it quickly? No. You can only check, if the question says find the best possible tour, there's no way to check it. But suppose the question was, is there a traveling salesman tour of cost less than or equal to 100? Now you can check it, right? That's why when we phrase these things precisely, you phrase them in the form to prove it's an NP, you make it as these yes-no questions, okay? Is it greater than or equal to a bound? Now, if I was able to quickly give you a tour for less than or equal to any bound you give me, I've got to be able to find the right tour, okay? So it's sort of a similar problem, but it's one you can check quickly.
Binary search the amount, so I cannot find it.
So you're saying you could binary search the amount. So what does that mean? That means that if I could answer my yes, no, is there a tour of a particular size or not? I could use that to find the minimum size tour by binary search. You're absolutely right. So if I can prove that my yes, no is at less than or equal a bound is hard. What does that mean? If my algorithm was fast, my yes, no algorithm was fast, I would be able to solve your version. Okay? But my version of yes, no is hard. So I can't use this strategy to solve that problem. And if you think about it, the problem of finding the tour, you're saying the best tour is very closely tied into, can I tell, is there a tour at least this good? Okay? The guarantees that I get are usually on these yes-no versions, so I can check them. But for thinking about them, I was playing fast and loose, because I think it's easier to think about the max or min versions of the problem. Any other questions about NP completeness or anything else you've wanted to ask? Know about NP completeness, but we're afraid to ask. Yes?
What's the current state of what was the most recent advancement on this problem?
What is the most recent advancement on this problem? This is P equal to N times P, this has pretty much been solved. But for the question of P equal, the question of is P equal to NP, what are the most recent advancements here? My understanding, this is not an area I work in, my understanding is that this is an area where there has been very little progress, okay, of trying to prove whether that P is not equal to NP. One thing that you hear about in the news that you might be curious about, have people heard about quantum computers? There's this vision that quantum computers can solve amazing things. They can factor big integers. You may have heard that, right? Now, does that mean that quantum computers can solve NP-complete problems? Well, factoring a big integer is like graph isomorphism. No one has actually really proven that that problem is hard. And in fact, there's good reason to believe it's not NP-complete. So quantum computers can solve factorization, but that doesn't give me all NP-complete problems. If you could build a quantum computer to solve satisfiability, the game would be over. Everything would be great. But all you can do by the quantum computer is break RSA or something like that. Yes.
The other thing is like it doesn't really like lower the complexity of the algorithm. It just like divides the 2 to the n to like 2 to the n divided 2.
Okay, there are ways of using quantum computers theoretically to help solve NP-complete problems, but they're not gonna. They don't make the big leap that you would dream of.
Polynomial
Yeah.
polynomial times.
So NP completeness remains important even if we get big quantum computers.
There are
Okay.
some problems where it goes from exponential to linear. I'm pretty sure.
You know, like sorting, factoring is the mother of all quantum computing problems. Any other questions about NP completeness? Can I live my life assuming P is not equal to NP? And but I think about a lot of problems through through this thing. Okay, any questions? Okay, I wanted to conclude just with a few remarks as I'm teaching. First, I wanted you to say I have enjoyed teaching you guys. You have a lot of enthusiasm. I see you in the morning. I don't see my own students in the morning. I have appreciated your questions, many of which are very good, and your attention. So I thank you for that. I also would very much like to thank all the assistants that we have here and the organizers, Rafael and Carlos, and anyone else who I have not forgotten. But this was a lot of fun. So thank them anyway. I think this was good. The last thing I want to talk about, just to you guys, unless someone wrestles me from the stage for the next 14 minutes, is a question of what you should do with your life. Okay? So, a small question. Okay? And, you know, it's clear that all of you are bright people, and all of you will go and be successful at, you know, whatever you basically choose to do. This much I clearly think. Most of you, I expect, will go into industry. Okay, let me do a quick test. How many people here are planning to go to industry after they finish? Seeing a bunch of people. How many people are thinking about going to get a PhD and go do academics? Okay, more, good for you, okay? Again, good for you if you're going into industry as well. There's no reason why being a professor is better than working for having an honest living, okay? But, so, you know, the question of what is the best thing for you to do is up to you, you know, and where you want to do it, it depends upon, you know, a lot of, the best life for you depends upon how you value career prospects and economic things and family access and lifestyle, what you like to do. And the best thing for you to do and the best place for you to do it is 100% up to you, and everyone should come up with a different answer. That said, I'd like to address a small subset of these questions of whether or not you should go to grad school. Okay? I've been hearing from talking to the professors and to some of you guys, you know, with skills like yours, you guys should have no trouble getting good jobs in industry as an undergrad. That said, I do believe that someone with undergraduate skills, even if you are an ACM ICPC champion, the world changes with time, okay? And, you know, what the best technical, you know, what the latest technologies are and what the latest ideas are. You don't tend to see that in industry in certain ways. When you go off to work, you're going to work for a company. You're going to focus on a particular product. You are going to become the world expert on the internals of that project. People at your company are going to love you for it, but you're going to be focused on your world is that product now. And the world outside is changing, and, you know, you've got to, you know, you'll see. So with time, people's skills tend to atrophy. The world changes, they don't change, okay? What I have found is that generally speaking, from my students, the students that get more interesting jobs at somewhat higher pay are those that have higher degrees, master's degrees or PhDs, okay? And if you decide to go for a graduate school, I think doing it when you are right after you do your undergrad is the best time in general for most people because life intrudes. You will start to form a family, okay? You will start to get used to having a real salary, okay, when you work for a company, okay? And suddenly being able to give that up after a couple of years is a harder thing, okay? So this may or may not be something you think about. Again, no law any of you have to go to grad school, okay? You will all have good lives without it, but some of you will have better lives with it. The next question should be, should I go to graduate school here or in my home country, or someplace someplace else? Okay? And one thing that I will say is it's clear that, again, I've been now teaching for more than 35 years. The world changes, okay? My skills have atrophied, as by everything I've said here. It's clear that the programs in Brazil and other countries are getting stronger, okay? On the other hand, it's still the case that the best computer science programs in the world are, generally speaking, outside of South America, okay? There are many in the United States, there are many in Europe, okay? I tell my students, when I have undergraduates at Stony Brook, we have great some of our undergrads are great, some of them are less great, okay? The great ones we always would love to have as our graduate students. I always tell any great undergrad I have at Stony Brook that they should go for their graduate degree someplace else other than Stony Brook. Why is that? Well, if you stay at Stony Brook and you took my undergrad algorithms class, guess whose graduate algorithms class you're going to be taking? Mine, and you're not going to learn as much. If you took it from somebody else, Corman's grad algorithms class is going to be different than mine, okay? So I think that there are a lot of reasons why, if you're going for a graduate degree, certainly a PhD, and usually, but not always, often, but not always, a master's degree, it's better to go to another university. This is my belief, okay, because you get exposed to different ideas. Certainly for a PhD, you should go to a different university than where you were an undergrad. This I believe pretty strongly. It may be different in some countries, and you can fight with me, or you can discuss it with me afterwards if you want. But certainly in the United States, this I think is absolutely true. I think it's a sin for them any of our undergrads to stay for a PhD there. And when you go to a PhD program, I encourage people to go to the best university they can get into that's in a place where they feel they can live, okay? You have to feel you can live there because you're going to spend 5 years there. And if you're can't live there, you're going to have a miserable 5 years. But I think that going to a good place makes a big difference, okay? Any questions? Yes?
I would like to know if you, as a professor in Stony Brook, and as a person from outside of South America, do you think it's hard to get into like a graduate sponsorship or something? Do you think it's hard for like a...
Okay, so the question I think is about money, ultimately.
Yeah.
Okay, so let me talk about the money thing. Because again, it's been a little bit of a surprise to me because we used to, in our department, get a lot of very good, we had a bunch of very good Brazilian students. Two of whom I know are now professors at NYU. There's another one who went on and apparently became a big shot at a company that owns a big, a big company. But we don't seem to see these students. I don't see these students so much anymore. And one reason I keep hearing is money. Now the money surprises me. Surprises me. If you apply to any decent university, a PhD program at any decent university in the United States, Stony Brook is well above the decent line by this measure, okay? We will pay all of our students, PhD students that we accept, full tuition and a living salary, okay? So the financial issues, I don't really understand the financial issues. If you get accepted to the PhD program at Stony Brook, you get free tuition, and these years you get a $36,000 a year stipend. okay, as a teaching assistantship and then a research assistantship. Now, this may sound like a lot of money to you guys. It'll sound like a little less money once you get to America and you see what things cost. But our graduate students live reasonably well. They eat better than what I'm about to eat lunch with you guys again later, okay? Graduate students will have a car, okay? Our graduate students can do certain things, okay? Our PhD students get summer jobs at, the best of our PhD students will get summer jobs at good companies like Google and Facebook, okay? And they will pay them real salaries. So you could think of that's 36,000 as a lower bound if you're going to get internships. I recommend my students go off for summer internships every summer because I think they learn something at these places. But different professors may disagree. We'll take care of it. The PhD model in the United States is a little different than Europe. And I think European PhDs tend to be shorter than American PhDs, okay? Which has pluses and minuses, okay? I generally think that that university, things in the U.S. are good. Okay, I thought I had a slide. Yeah, here was my slide. I personally think, and again, I'm biased as a U.S. person and stuff like that, but I do believe that research at the top U.S. schools are in many ways kind of, they get into a lot of, you can get into any exciting area that you want. People like AI, people like quantum computing. And I think that in the U.S. there's kind of a mix of, there's a level of interaction between companies and universities and research problems and government funding that kind of promotes people working on exciting things that may be different than other places. So I think that there is a reason why universities, great technologies get developed in the U.S. And I think it's kind of a mix between, kind of the incentives and the way universities work and so on. And I think getting that culture, I think, is a good thing. But the finances, like I say, if you want to get a PhD in the United States, the finances should not be a problem. I don't understand why that would be. Whether you will get admitted to the university depends upon your skills. I think you guys are probably pretty good. But if we want you enough to pay for it. Okay? Question?
Is it easy to get a PhD position without having a master's degree?
Okay, can you apply for a PhD without a master's degree? The answer is yes, okay? A PhD program kind of implicitly, many of our students get a master's degree kind of as a sort of a sub-prize as they come through the way. So theoretically, it will take you more time, I guess, without a master's degree, but that's still somewhat theoretical. If you come to me with some master's degree from Mars and you're taking my, I'm only going to be impressed if you're doing well in my classes, and it's not clear that I'm going to think you're more advanced. Hopefully you're more advanced. But we don't think too much about the difference between our PhD students that have master's degrees and don't. We do like our PhD students to have some research experience at home. But frankly, I like students that have the ICPC experience, okay? And this is a debate level. But if you're saying, hey, I was on a team that made it to the World Finals, okay? That is a substantial credential, okay? And if I got an application like that, I would take that application seriously. Other professors on the admissions committees might view it differently. Why didn't he write a research paper instead, or something like that? But I think that that's a credential that is a measurable credential, okay? Any other questions about grad school or the processes or anything like that? Okay. Okay, if anyone wants to talk about it, that's fine. I guess the last question, should you go to Stony Brook? Obviously, if you're going to apply to PhD programs in the United States, you should apply to a bunch of them. Which one should you go to? I told you this earlier. Which one should you go to? The best one you get into. Okay, so that's certainly true. You know, there's sometimes you may say, oh, there's a particular advisor I love and I want to go with. Maybe, okay? It may be an area that you're special with, maybe, okay? But anyway, again, if any of you are interested in Stony Brook, please feel free to mail me. This is my official Stony Brook mail. I'm also at skina@gmail.com. If you want to send me mail, make sure early in the note, email, it mentions, oh, I took your class at the IOI thing. So I know not to ignore it like I ignore most people's mail, okay? And if I do ignore you, try again, okay? Any questions about that? If not, I'm going to be rooting for you, Brazil, in the World Finals, okay? So good luck, and it's been fun teaching you, and I'll root for you. Eaten with, I'll have lunch with you. So if there's another group of people here who I didn't eat with yesterday or the day before, but wants to eat with me, okay, I'm happy. Come back here and I'll be happy to go to lunch with you all. Okay, thank you very much.